Therefore, that's second one. And third is something about fabric thickness and thermal resistivity. Usually they are saying nano are better for better thermal insulation. We can see it is not precisely valid because thermal insulation depends on the thickness. And we can see this graph is showing you thickness of air layer with some of lowest thermal conductivity, therefore very good thermal insulation. And it is required thickness for some cloth. Therefore, we can see if we need some cloth 4, we should have a 5 millimeters. Therefore, we cannot have a nano layer. Nano layer will be, if it will be composed only from air, will be not sufficient. Therefore, we can see in some instances that nano is only to promote or to support something, but alone cannot be used, will be efficient for applications. Therefore, we can see in textile necessary to discuss some thickness, necessary to discuss some properties, and after then we can decide if it is a real benefit or if it is only some story. And now some nanoparticles. Nanoparticles are used practically everywhere. Some of them are very popular, some of them are beneficial, some of them are not so popular. I will show you our successful cases according to nanoparticles or nanomaterials. I select 3 kinds of materials. All are multifunctional. One is titanium dioxide nanoparticles. We have plenty of interesting effects: decolorization, anti-fouling, antibacterial, UV absorption, self-cleaning, water cleaning. Therefore, there is plenty of possibilities dealt with that material. Therefore, that's one case. And on that corner, we can see practical application. One is natural cleaning of some lamp used on the roads. On the right is typical pollution from the dust. On the left is titanium dioxide finishing. Therefore, we can, or surface modification. We can see it is after some time some self-cleaning system. On the corner is some antibacterial tiles from with some nanostructure as well. We can see bacteria are killed. Here is some decolorization of water with some dye stuff as well. We can see after some time we have decolorization. And here is some anti-fouling system. Part of mirror is standard, and second part of mirror is with some titanium dioxide. Therefore, they are beneficial. And I will show you our approach or our possibilities how to enhance this one. Second are carbon nanostructures with some electric conductivity, emission shielding, resistive heating, bad smell capturing, anti-static. Therefore, as well multifunctional. And I will show you as is simple to obtain these effects via some thermal treatment. And third is surface deposition of some copper nanoparticles, as well similar as carbon nanostructures, but we have at least some novelty as reflection of far infrared radiation, antifungal, and that's necessary to say. According to this we have some certificate. It is antimicrobial, but in plenty of cases is no antifungal. And necessary to say, for our body, most danger are fungi, not bacteria. Therefore, according to our skin, and that's antifungal is necessary. Therefore, it's better to test these properties, and we found plenty of standard antimicrobial are no antifungal. Therefore, it is necessary to mention that. Therefore, according to titanium dioxide, we create some system to tune some size, especially preparing some particles with small size and some crystallinity from that. It is described in some publications, only showing particle distributions is standard titanium dioxide P25 from Degussa is approximately 20 nanometers. In our case, we have 6 nanometers, and we can see according to decolorization that violet is standard material. Our approach is in fact 20% over or more than 20%. And what is reason? It is some kind of preparation via ultrasonification. Therefore, we can create another kind of particles with much better properties as compared with some properties on the market. Therefore, that's something like that.
Here are some more.
Yeah, I will have 20 minutes and I will finish it. Yeah. Second is some removal of dye stuffs as well. Therefore, as I showed you before, necessary to calculate these effects according to surface area because it is some filtering, not arbitrarily using. And as well, these nanoparticles are much better. Second are carbon webs from some wastes. Probably waste treatment will be very important, and we can use carbonization of practically majority of waste appeared in the textile area. Much simpler is to use acrylic because from acrylic there are creating standardly carbon materials. Therefore, it is beneficial. And what is our approach? We try to use some conditions for pyrolysing, and based on them we obtain very interesting effects. We can see here we have images of that pyrolysis 800 degrees of Celsius, 1000 and 1200. There are some differences about crystallinity, there are some differences about relative surface area, and major differences are in electrical properties. We can see in case of electrical properties, via increasing of temperature of pyrolysis, we can obtain higher and higher conductivity, therefore less and less electric resistivity. I will show you it on the figures. Here are some figures according to electromagnetic shielding. We can see at 800 degrees of Celsius, we have a 5. It is the same as in classical materials. Therefore, if you'll be using polyester, polyamide, it is 5 or less than 5. In 1000, we have 30 or 35. And 35 is very good electromagnetic shielding on the level of very advanced materials. Therefore, we can see only changing of temperature, we can obtain very good materials according to these properties. Second is some figure showing you this shielding based on the frequency. Usually we should discuss about some 8.0 gigahertz, 0.4 gigahertz and that. And we can see as well, in low temperature, it is practically no shielding. In a high temperature, it is very huge shielding. Depends on the frequency. Therefore, it is possible via this technology to change these properties. Third picture is showing you some resistive heating. Therefore, we used some source with some voltage supply, putting on the both end and heating. And we can see it was possible to obtain temperature 33 was as an ambient temperature. And we can see we were able to obtain via tuning these materials to have a temperature at 1.5 volts, 83 to 200 degrees of Celsius. Therefore, it is very good for some kind of ohmic heating, and we can tune that materials if we need to heat our legs or if we need to have our walls. Therefore, it is possible to modify it. And question is only temperature of pyrolysis, a little bit time. Therefore, it is a simple way how to obtain that or how to modify that. And only depends if you have some source with these high temperatures. And last from that is some iron impregnated materials. In that case, it was possible to activate surface area with, in fact, doubling relative absorption ability. Therefore, as well, via some small modification, via some materials, it was possible to obtain that ones. Third is a very interesting system based on so-called milliphy or milliphy. That material is some kind of composite nonwovens. That composite are two layers. One is in that direction, second is in cross direction. And based on some high magnification, we can see some joining spots being created from some melting part. And we use these materials for covering via some copper materials. I will be now following some technology, what it is, but we can see there are some particles on the surface of materials. And here are some properties. We can see fiber thickness is practically very low. GSM is as well, 11 is practically nothing. And we can see resistivity is from 10 powered by 13 to 10 powered by -3. Therefore, very huge increase of conductivity via these kind of particles. And as well, we can see here, when we will be using that materials for electromagnetic shielding, here is practically 2, 3, therefore nearby 0, and here we have more than 50. More than 50, and GSM is 12. Therefore, it is very narrow layer with very good electromagnetic shielding. Somebody could be asking me why we need electromagnetic shielding. We are no influence to some parasite or something like that. It is simple. If you will be using that for covering of your mobile, nobody will be able to identify where you are. Therefore, it is one possibility. Second is you will be covering your credit card by that. Nobody will be able to read what is in. In opposite case, they have some mobile applications being able to read your card through some standard cover. And third is as well in laptop, if you'll be having covering of your laptop, nobody will be able to identify if in your car is laptop or not. Especially in Europe, there are some thieves being able to identify a laptop. If it is in, they are broken car and withdraw laptop. Therefore, we can see that applications could be not standardly textile, but very useful. Here are some effects of aging, no probably necessary to follow. Here are some influence of milliphi if it will be higher GSM. Here are some layering system. And here are some possibilities to see how is, in fact, effect of this material on some reflection of some radiation simulating your body. Therefore, we have some source of energy, thermal energy, with temperature of 40 degrees Celsius, ambient is 23, and we are measuring via thermal camera what is passing through that 30 source and this material layer. And we can see we are able to obtain 60–70% being reflected back. Therefore, this material is very thin, but is able to reflect majority or at least more than 1/2 of your heat producing by your body back. Therefore, as well, thin and working. And I have still some, some slides about nanomaterial toxicity. Only necessary to say what is here. All substances, including water, are toxic, depends on the amount and some conditions of exposure. Therefore, cannot be saying something is toxic, something is not toxic. We should discuss about those, we should discuss about conditions. In case of nanoparticles, there are two troubles. One is, due to nano, they are able to penetrate through human cells. And everything in your human cells is, in fact, not good for you. And second, in some cases, we have a positive charge nanomaterials, as are metallic parts and reds, and our cells are negatively charged. Therefore, we have natural attraction to that particles to our cells. Therefore, we can see it is necessary to discuss precisely what it is. And as I said, nano, according to effects or health effects, are still necessary to be discussed. Last is some kind of surface reactivity. Therefore, that materials are more reactive, and that materials are better deposited in our body because microphages are not able to withdraw them. Therefore, we can see some chronic actions are appeared. Therefore, probably it is everything from my side. Thank you.
Thank you, Professor Militsky. This nano, its application, its your future. At the same time that what he is trying to find out, there are certain myths that has to be seen, how and this all positive findings are not the research, negative findings are equally a good research. That is the message what Professor Militsky has tried. And one of the myths that I have, that also particularly a good number of people here in yarn manufacturing, one of the myths that we measure the fart by weight. Is it true? Our evenness tester is measuring the fart by weight, mass, which is totally wrong. Fart has always dimensions. So this is another myth that we have to correct. With this, now I will invite these two questions from the audience, please. Professor Sharma.
What areas of application you prioritize for commercialization?
Of that, I showed the effects. Therefore, for example, I will be starting from the last one. Therefore, about these MILIF covered by copper. We have now some company in Czech Republic, chemical company producing that materials industrially. What is interesting, motivation was some passport. They said they need something of covering of passport. Therefore, they started with that. After they found all kind of these envelopes on covering of some materials are good. And still we are discussing with some people from military orientation, because combination of that with some carbon, it's possible to suppress, for example, of your infrared radiation. Therefore, you will be not visible in infrared region, or cars, when they will be stopping, they could cover that by this layer, and it will be not possible to identify them. So for these kind of camouflage effects is as well promising. But they are using till yet only carbon, but carbon is absorbing. That one is reflecting. Therefore, if you will be having both layers, could be some enhanced effects. A little bit, yeah, but we are trying, especially because in some cases, as is these kind of covers, and that is no washing. If we are using it for textile applications, we are using some silanization. In that case, it is a little bit 10% less effects according electromagnetic shielding, but still sufficient. And via silanization, we have a permanent effect. In case of conductivity, it's not so simple, because if we will be covering something via silanization layer, it is not conductive. Therefore, we are not having so good electric conductivity. We could activate it via some degradation, surface degradation, to unhide some particles. But electromagnetic shielding is question of thickness, and in case is functioning.
Any other application area other than the defense and automotive, which you have talked about in Czech Republic? Can we look forward for that?
No, according to these electromagnetic shielding or these conductive materials, according to titanium dioxide, it's very simple, because we are able to practically remove this P25 from Degussa by our one. Therefore, it is, we will have another powder, and Degussa is producing them for plenty of application. Therefore, it is only question of who will be producing it in industrial scale. Yeah, therefore, that's. But we are, as a country, very small. Therefore, our capacities are not able to cover the whole market. But it could be used instead of standard titanium dioxide nanoparticles. It's possible to use these particles, because effect is much higher or much intensive.
Thank you, sir.
Thank you.
Okay, thank you, Professor Militsky, for his really very informative lecture, and big clap for that. Now I will request the organizer to complete their other task.
A memento being given to Professor Militsky by Dr. Ishtiaq. And there's also a gift hamper from Perth.
Okay, so now next lecture, this is by Professor Bhuvnesh Gupta from IIT Delhi. For a good number of years that he is talking area of medical textile. What today Kamal Mishra has said, that till that child is taking a naked birth, I say till the death is going to be there, that one will use again textile. So textile is from birth to death. That is the journey of textile. With this, now that how to enhance or reduce this death, there that I will now call Professor Bhuvnesh to talk about the application of textile in medical.
Can I use your bottle, Chairman?
This is for you only.
Thank you so much. Okay, so let me say thank you to Textile Association for giving me this opportunity to be here with all of you. A nice interaction, and especially having eminent textile person sitting here as chairperson. So the day is good, the day is very nice for me. Now we have been in fact working in the field of textile or medical textile. Within medical textiles, we have very specialized area, that's biomedical textile, or we call it biotextiles. So these textile materials are really interesting because we have enormous possibilities as far as these different applications are concerned. So what happens in biotextiles, okay, so what happens with textiles, you have the materials, polymer materials, and what you do is combine with bioactive components. And this combination of two things together, this gives you the biotextiles. So this is how this new area, relatively, I would say, recent area of biotextiles within the domain of medical textiles was created. Now, there are enormous possibilities, enormous applications where these textiles are being used. You can say protective textiles, surgical gowns, surgeons wear masks are there, hygiene products are there, napkins, towels. But at the same time, there are applications where these textile materials are used in close contact with the tissues and cells. And that's how these are like implants are used in the body. There are materials, sutures are there, heart vascular grafts are there, hernia repair, hernia mesh is very, very well-known product which is out of polypropylene. So these are the materials which have different applications. And this is where I'm going to confine my discussion on the last two, because they're really interesting because the material is always in contact with the body tissue, and that makes difference as far as the application of these materials are concerned. But then, if you see the importance of the material, why these materials are so important, the interesting part is that population is growing. And not only the population growth, but also each of us are always interested in products which are going to deliver better performance at the site, and at the same time they have newer or innovative features in there. So this combination plus the population growth, the market for biotextiles has grown up. And in this whole domain scenarios, we are working in 4 very specific areas. This is first the wound care systems, so wound dressings, that's what we call it. Now these wound dressings, that means you have to take care of the wound to provide proper atmosphere, environment for the healing of the wound. The tissue engineering is another domain where you can reconstruct, you can design your body part in the laboratory and fix it back to the body. This is a very fascinating domain which was initiated by Professor Langer in '89. So 30 years, it has given a beautiful thing. Then we have sutures. These are the filaments, threads, which are used to tie tissues after each surgical procedure. So very interesting materials. And then catheters are also, these catheters are the materials which are used for, especially urinary catheters, whenever their surgical procedure is carried out. So if we look at on all these areas, the materials may be the same, but what happens is that the requirement or the features in the materials may be different. And this is how you have to go for a specific consideration of features for designing these biotextiles or medical textiles for these applications. Now, if I start with tissue engineering, as you say, this tissue engineering is normally what? This is, we call it the alternative to transplantation. Because many times what happens, you have to go for the donor, and many times, by the time donor is there or available, the patient is dead. Not only that, but also in transplantation, what happens, if you take the tissue from some other person, the rejection is a serious problem. So you have to take care of these things. This is where the tissue engineering has come a long way. Sorry. So what happens here is you have the textile patch, textile fabric. You can take out these cells by biopsy from the patient's organ where the defect is or cancer is. This biopsy tissue is then expanded into a specific number of cells, and then you grow these cells on the fabric. Now, if you do that, this growth gives the tissue. So whole thing, either you take away the tissue patch, transplant it to the patient, or else you take the whole composite structure of fabric plus tissue and put it inside. Now, if the fabric is biodegradable in nature, like polylactic acid, fiber filaments, it will go out of the scene, and what you get is a perfect patch at the site. So we started with urinary bladder. While I was working in Sweden, in Switzerland, we was working with Professor Hilborn, and there are problems with urinary bladder reconstruction. Now, urinary bladder, sometimes they're tumor. Now, you can't get a bladder from someone else. So what happens, you have to design something. Now, initially, people were doing is they were taking out the intestinal mucosa from the cadavers and all the other animals, trying to put it there, but that also did not work. So idea was, can we develop something new, something interesting, which will work? So what to do is, the important thing is about the knitted structures. The weft knitted structure, we take it, and then we can take out these healthy cells from the bladder, expand them, put it on the top of this fabric, and ultimately you can grow it. Now, but where is the science? And you can see that if you do that, the patch, white part, you can see that a small tissue, a 1 millimeter, 2 millimeter by 2 millimeter patch gives you 5 by 5 centimeter live patch, because we could grow the urothelial cells on top of it. And this is where the technology comes in. Now, that is important. If you take out the cell from the body, if you take out the tissue from the body, try to put it in polypropylene fabric or polyester fabric, it will die. So as a textile scientist or a textile engineer, our job is to develop the fabric which will not allow cells to die. It will give the atmosphere so that cells could grow over there. Homely atmosphere, as if cells feel as if they are in a homely atmosphere. And this is where the technology comes into picture. We need the collaboration of biomedical scientists, we need bioscientists, material scientists, textile scientists, medical people, surgeons. All these people together, they are going to produce structures like that. So it's a collaborative activity with all these people together. So the success story which we started 2000, almost 2000, 2001, Professor Hilborn. We got a lot of funding from DBT for blood vessel reconstruction, especially when there's a bypass surgery. You take out the saphenous vein from thigh, put it there. So when there is multiple surgery, can we develop hollow structures out of these textile materials? So what we did, we had the braided structures of textiles, very innovative materials, and these materials we seeded inside by the endothelial lining. Now, if blood flows through this endothelial lining, what will happen? It will see the endothelial lining, not the fabric. So ultimately, the scaffold which we made out of the braided structure, that does the job. We did this experiment under collaboration with France in 2015, and you can see we replaced the aorta. Aorta is the one which starts from heart, it goes down to the kidney. So we replaced 2 centimeters of aorta by our tubing which we prepared. And I can tell you, the mouse was alive for 3 months. So this gave us a lot of things that, if mice can stay for 3 months, maybe, we have much more possibilities. So Jinsi Joy, she's my PhD student. She's working on this product, still working with me. Then subsequently thought, why not move to some other body parts? And this is how we started collaboration with Sikkim Manipal Medical College. That's in Gangtok. So we started working on it. So we thought, why not develop these materials? So we had gelatin and other similar systems, made the electrospinning out of it. You develop the nanofibrous mat. And this nanofibrous mat, we seeded cells from the skin. See, especially burn patient, you have to take away skin from other part and put it there. That's all not very, very interesting. The other part is then damaged. So we tried to put that keratinocytes, melanocytes together. We wanted seed on top of it. We could do it. And I can tell you, we could grow from few cells we could grow the whole structure of the skin, which we can take away by the forceps. So this is something which is very interesting. We're still working on it to see how the color and other things are coming to this. But it opens up enormous possibilities for human organ reconstruction. Now, there are many applications like that where the problem is the infection. Now, the infection, you see the possibilities. Sutures are there, hernia repair is there. Hernia repair is there, hurt valves and stents are there, wounds are there, wound care system is needed. So what you see is in everywhere you find the infection. Now, infection looks very simple word, I tell you, but this could be really problematic. Sometimes this infection can give you septicemia. That means amputation has to be carried out. So this small thing of infection could be really fatal. Now, this is where the important thing is. As a textile person, our job is to design these materials which are having proactive role. These materials, if they do not allow bacteria to grow, stay, then I think your job is done. The bacteria cannot stay, bacteria cannot grow over there. This is how we are working on the systems for many applications, especially the wound care system. This is what I'm going to tell you. In wound care system, what happens, you need the covering or dressing, which is sarvaguna sampan, that's how we call it. It should be able to absorb moisture, exudate from the wound, should be infection resistant in nature, should be biocompatible, because this is always in contact with the tissues. So we try to work together, say things which can give you all these possibilities there. Started working with biopolymers. Biopolymers, very interesting polymers. You get them from nature. Pectin is example, chitosan is example. So we took biopolymers like chitosan, beautiful material you get from seafood processing industry. And this chitosan we combined together with PVA and polyethylene oxide, because chitosan film, if you want to make, is very hard. In contact, the tissue cannot stay there. So this combination we try to put together in such a way that we get the membrane-like structure by coating on a fabric. And if we do that, there is some ingredient, and that ingredient is bioactive components. What will happen? If bioactive component is there, it will release from the system, and this bioactive component will take care of the infection at the site, and the healing will also be there. So the question, where is the choice of bioactive component? What should we do? Which bioactive component should we start working with? There are enormous possibilities. Again, if you see the interesting world, people were using antibiotics. Tetracycline is one example. These antibiotics are there since so many decades. But then slowly people are moving to herbal stuff. Aloe vera is one. Curcumin, which is called haldi, that's another thing. Neem oil is another thing. So, and more recently, silver has come up. Many people are working on nanosilver. So these combinations are there. It's your wisdom which polymer to choose. It's your wisdom which bioactive component to choose. And the process is very simple. If you have to take this whole fabric, you go for padding mangle. And by padding mangle, you can coat these materials on the fabric surface. And at the end, you get the material which is really, a fascinating material as far as the wound care is is there. The first one you can see dressing, which is out of aloe vera. The second one is out of curcumin, because haldi is yellow in color, so that's why you see the yellow color there. And these dressings, herbal dressings, were prepared by my student, Rupali. She is now in the US, working over there. And we thought, let us see how it happens with this combination, this biopolymer, bioactive component combination to the wound care systems. If you see the antimicrobial nature, infection, first thing in acute or other wounds you have to do is you have to stop the infection. If you can't stop infection, you can't give the healing to the wound. So we thought, let us see if this aloe, So you see that 40% aloe vera in the dressing gives almost 90% reduction in colonies, control of infection. So you can see that this is slow. Not like antibiotics that you get 100% within a day. It's slow process of using aloe vera, but doesn't matter. Instead of 2 days, if it takes 4 days, you're having a system which is excellent system because there are many more possibilities as far as these materials are concerned. Now, in these possibilities, I like to say that we are working on a system where scar formation is a real problem. Whenever there is healing, it's always scar formation. Now, if you can take care of scar, sometimes it's on an open body part and very difficult to really digest it throughout the life. So if you take care of scar formation, together with the healing part or within the healing domain, I think you can do a wonderful job. So we are working on kite system. My student, Dr. Sadia, she is working on these things. And we developed the material by coating onto a cotton fabric. So these systems are made porous in nature. Now, porosity helps in what? If you use your dressings on a wound, the porosity helps in the exudate absorption. So we developed these materials, and I can say a wonderful results that we found. We are working together with Jamia Hamdard for animal studies. But you see, it's real proper control of scar formation. The first one, you see the fresh wound, and after 21 days, it was really difficult to find if at all any wound was there. 58% scar formation in the first case. At the end of 21 days, we had 2% scar formation. And this is what we patented. My student, Dr. Sadia, she has made a patent very recently out of it. So you can see that these are the innovations. As a textile scientist, it's not only the healing of the wound, but also the way the healing takes place. Healing should take place without any scar formation. I think you can do a wonderful job to the human healthcare systems. So with these things in mind, we thought, okay, if herbal systems are so good, why not move to some more possibilities? So we thought, okay, let us move to the acne treatment. There are a lot of problems with our young generation, acne, etc. So we thought, okay, let us do that. So we started working on different other bioactive components. And this is where Prashansha, she has been my project staff. So we started working on tea tree oil and clove oil and other things. And you can see that with these materials in mind, ciprofloxacin is there. We have combined this cipro, and even, you can use ciprofloxacin also. So if you combine these things together with other systems, we do not get any infection. Colony formation, hardly any colony is there. So we have proper control over the infection. Similarly, not only these things, biotic components, if you want to move to something more interesting, if the wound is really in a very acute condition, you can use silver also. So we thought we can do that part also. So you can use silver and other things. And this is how the Gale gave us this project 3 years back. We patented this whole process where you can develop the fabric by using the nano silver-based technology where the infection could be easily controlled. And it's a really great thing to see that, how the infection is controlled. If I show you this scanning micrographs, you can see over here, this side is full of bacteria, SRS colonies. You see, on the fabric surface, filament surface. The other side, which is modified by our nanotechnology using nano-herbal components, other components, hardly any bacteria stays there. So if bacteria is not staying there, the infection problem is already taken care by us. And these materials is always question. I mean, we are showing the bacteria is gone, but what about in contact with the tissue? So we have to always, any process which we do in vitro, we have to go for in vivo in animals also before any commercialization could be achieved. So we went to the other thing, which is the animal model with the CO stand of clove oil and manuka honey. Honey is also a beautiful thing. I tell you, beautiful things are happening. In both the cases, you can see that clove oil at the end, it gives perfect, very good healing process. Although honey is also good, but not as good as the clove oil. So you can see a combination of different things which are there, they are there. But then, question is, if we have these materials, can we go to the other possibility, which is the nano? Because nano gives you an option to use much smaller amount of the bioactive component. So this is how we started working with nano, like nano zinc oxide, nano silver, and other things. And all these things, I tell you, they're excellent materials for the growth. You can see over there in E. coli, in case of E. coli, the zinc oxide is on the top, the other on the nanosol on the other side. In between, you see the colony formation. But in case of zinc oxide, nano zinc oxide, and nano silver, You do not see any such thing. But the question is what? The question is different. You have the nanomaterial, and you have surface. It's fine, it can attach, but how to attach it? If the surface is not receptive, how to attach it? If your nanosilver try to put in PP non-woven, it will not attach because PP has no receptivity. So this is how we thought, even the nanosilver has no bonding, no possibility except the coordination bonding. So we thought if we can develop a nanosilver with the coating around, nano coating around out of some polymer, which is functional polymer, our job is done. So this is what we had started working a long back, few years back, where we developed these materials where we could have the nanosilver and we could create a layer, nano layer of other polymeric materials so that these polymaterials have carboxyl, hydroxyl, other groups, and you can attach it to the server. And you see the nano particles over here, 10 nanometers, 20 nanometers, 30 nanometers, depending on the size. Nano gels, we call them nano silver, nano gel, because this nano silver, this nano within nano, so nano silver is within nano gel. That's how we call them nano gels. And they are highly interesting materials. They can attach anywhere, even by encapsulation. Anybody can think that when you make a covering out around the nano silver, this may not be effective, but I can say that they're very effective. You can see on this side, 4 minutes contact with nanosilver, the bacterial colony, cell wall is ruptured, protoplasm has come out, fusion of the colony, E. coli taking place. So what I'm saying is, even if you have a covering of a nanogel around the nanosilver, the material is equally good as far as this thing is concerned. But then you can fix it on any fabric. Here we used cotton, I think, but then this is the coating which we carried on these fabrics, and we tried to see if these materials are good enough or not. But then within the hemostatic, another thing which is very important, especially for army, they go to battlefield, and if any limb or anything is gone, there's excessive bleeding over there. So can you control the bleeding of these materials? Can you control things over there? This is how we are working on a system where you need to control the bleeding of the part by using different hydrogel-based systems. So not only the control of bleeding, because the people, soldiers are in a very hostile environment, lot of infection. So you have to control the bleeding, you have to control the infection also. This is what is a recent activity which we are doing in our group. Now, as I said, you have the nanosilver, you have the functional nanosilver, which has got the material out around. How do you fix it? For that, PP, suppose we have the PP, how do you fix it? So this is where you have to functionalize the fabric also. And this is done by plasma processing. It's a beautiful technique, I tell you. This plasma processing of textiles, you can create different functional groups depending on the carrier gas that you use. That means if you use what? Suppose you use argon oxygen, you create hydroxyl groups. You use ammonia, you create NH2 groups. You use carbon dioxide, you create carboxyl groups. Monomer, you do anything. That means these materials you create on the surface. On the surface, you make the polymer or non-woven material receptive to any functional group. And you can see over here, pristine fabric on this side, 60 seconds plasma. The drop stays there, but 16 seconds plasma, drop doesn't stay. It's completely gone inside. Such a high hydrophilicity is created. In 60 seconds, your hydrophobic material converted to hydrophilic material. I don't think we can have any chemistry which can do this wonderful job if plasma is not considered. So these things are very important, very interesting. 5-6 minutes maybe I have?
Only 5 minutes.
Okay, I'll finish it at that time. Good. So you can see these things that fabrics, by plasma processing, immobilize them. On this side, a lot of colony formation. Other side, you don't see any infection formation. Now, this technology, plasma processing, we are working since last 16 years and trying to develop new and new products. One of the products which we try to develop is the sutures. Sutures, these are the filaments. A lot of infection problems are there. Now, in big cities, if you go to Max Hospital, you are in a very air-conditioned operation theater. If you are in a village, there's no such possibility. And the infection is a serious problem in villages. So 80% people who live in villages, if you can create and develop a suture which will not allow infection, I think you can give happiness to all this whole mass of 80% population. So we started working on PP. which is the polypropylene, which is proline suture. And this, what we did, this proline suture we use by plasma processing. So process by plasma, create some functional groups over there, and then we immobilize. We immobilize bioactive components. It could be antibiotic, it could be other antibiotic herbal product, and many other things. So these materials, this is the patent we started in 2018. We have 4 or 5 patents on this technology. Sorry. So you can see these sutures which we have developed. You find that on the other side, white, this is unmodified. There's a lot of infection, colony growing. But the one which has got shaded portion, the shaded portion, no bacterial colony is growing there. So these sutures we've developed by plasma processing. They're wonderful materials, and they give enormous possibilities for using it in different locations. Even the animal tests which we carried out on the sutures, you can see that on this side, the top side, unmodified suture, see redness is there, some inflammation is there, some edema. Edema is the swelling, little bit swelling of the tissue. It's there, but in other cases where we use modified suture, plasma, modified suture, no infection, nothing, and wonderful thing that happened over there. And you can see over there even the biocompatibility healing. Dr. Sadia carried out this work last year on these sutures. We had a wonderful healing as far as the animals are concerned. And this part, so similarly, we could use these materials also, not only sutures, but also these materials on dressings. These dressings were, like you can see the fabric, this is in Gangtok study in 2015. So we had this healing part, and I show you again, beautiful thing that you can realize. A control sample healing is still there after 16 days with nanosilver, pure nanosilver. Healing is not yet complete. But number 3, if we combine nanosilver alloy, the healing is really good. We combine nanosilver with curcumin, healing is still not good. And at the end also alloy, 2 together is not so good. That's all I can say is the alloy is the best. Aloe vera gives you the perfect thing. The reason, it not only stops infection at the side, but also gives you proper healing of the wound. And this is what we needed. So to say that, these nanogels, nanomaterials, they really help a lot as far as the development of these functional materials is concerned. The only thing is that we need to develop these smart materials in such a way that they're good for the application. Human organ reconstruction is a beautiful approach that can be achieved by textile materials. Bioactive materials, especially herbal buns, they are the beautiful moieties which could be used for all these things. A lot of potential for human healthcare. Again, if you can go to the biopolymers, I think it's a wonderful scenario because these biopolymers, they are biodegradable in nature. They degrade by the enzymatic action whenever there is something in there. So with this, I like to say that media reports a lot of work that has gone to, even Astak made a beautiful documentary on the work that we carried out. And we had a lot of funding from different places, from Europe, Sweden, France, India. A lot of people are attached to other. From France, especially Hilbon, on the tissue engineering side, Didi Latourne, Amedy also from the biopolymer side, Philippe Roger and other people. We are part of it. The group which made this contribution. On this side, you have the nanotechnology. Other side is the wound care system. In the center, the students, they worked on human organ reconstruction by tissue engineering. With that, I'd like to thank you so much for attention. If there's anything, I will get from you.
Thank you, Professor Bhuvnesh, and we can say we are in safe hands of Professor Bhuvnesh. So he will take care of our health. That area, that medical, textile, in particular biomedical, that he tried to give emphasis. This is the area which say that the future investment is going to be in 2 areas, health and security. So textile has to penetrate in these 2 areas. These are going to be the future. How that textile has to move to medical and how this health or how textile has to move towards security and safety. These are 2 other areas. With this, I will take 2 questions from the audience, please.
Professor Bhuvnesh, this is regarding the stents which are commonly used in the body, in the heart and in the urinary system. So is there any biodegradable alternative available? Because at the end of the day, after a year or a couple of years, they have to be removed.
Stents, yes. Commercially, production is there for stents, but not for catheters, other things.
You mean biodegradable?
They're biodegradable, they have come out.
But
So
not
little
for,
bit progress
not for urinary system.
Not yet. It's not yet done because, for sometimes the catheters are used for 2, 3 days, 4 days. And by biodegradation, the mechanical strength goes down, other complications arise. But for stents, you need something which can stay for 2 years with little retention of medical tensile strength that works. People are working on it. Many possible, like hernia, PP mesh is used. But today, people are working on biodegradable hernia mesh also. So it's a dynamic process of invention and innovations which is going on together.
I think one question from that side, yeah, please.
Yeah. Professor,
Yeah.
as we learned when we were students, the cellulose is made in the atmosphere by combination of carbon and hydrogen. So when you are talking about making the hydrophobic material to hydrophilic, so again, basically, CH2 and the plasma you say. How permanent is that feature, beginning to end of the product, that it will be hydrophilic? The level of that absorption will be same from beginning to end, or after some it will recede?
Yeah, I tell you, plasma processing gives you the surface modification of, say, 5 to 10 nanometers on the surface. Now, this 10 nanometer, it stays there. If you are keeping it at lower temperature, minus 20, it stays there for months. If you leave it here, what happens? At room temperature, surface reorganization takes place because of the interfacial tension between the highly hydrophilic surface and highly hydrophobic. So they migrate into the bulk. But if you place them again in water, they will come out. That's what we have found it. So it's stable. I mean, it's perfectly. Functional groups is chemistry. They go nowhere. They stay there either outside or inside, depending on the storage conditions.
So one more question I will take because he raised his hand first.
Mr. Gupta, you just tell us before you work out as to which suture or which material is to be used for this, is there any compatibility test? Because what happens is not always necessary that the body organs may not react, or there can be any kind of allergic reaction. So is there any study on this?
Yeah, okay, yes, yeah, you're right. See, I mean, between laboratory and the hospital, there are two things. One is the preclinical, other one is clinical trial. Now, in preclinical, what we do is we do in vitro also. That way, in the laboratory, we go for MTT assay and other things and just see whether the toxicity is there or not. For any animal studies, we have to prove it to the drug controller that these materials are not toxic to the animal. Otherwise, animal is not allowed. So it's a process. We have to do, all these data are important. We did those things also, because we can't show you all those things here. So we did in vitro studies by using fibroblast cells and other cells so that to see if the material is compatible or not. And they're compatible, perfectly fine. We did even you can say that, we did histopathology also. We took out material from skin together with the suture, cut it to the specific slices, go to the microscopy and then see the growth of different types of cells. And we did not see any polymorph and other things, So really compatible. You have to make it compatible. It's not like every material is compatible. You have to process your material in such a way that it is also biocompatible. If you add anything which gives you reaction to the body, inflammation will be there, the material is gone. So that's the designing part. That's the chemistry part that you have to play around.
Professor, that for dialysis, normally they put in the collar or some tube. Have you been able to develop some matter which goes for a longer time? In dialysis, after 2 weeks or 3 weeks, there is an infection and we have to reoperate. And
till now, there is no such report for dialysis and other things. It's very complicated structure, dialysis. Kidney is very complicated, For other organs, people could make it. They could harvest your body parts in the laboratory. But kidney and other things, not yet. So,
thank you.
It will take time, probably some time. Yeah.
Thank you, Professor Bhuvnesh, and I think that he needs a big clap. Thank you very much.
Thank you so much.
Dr. Ishtiaq to do the honors again.
Thank you so much.